Hello everyone and welcome to the series of 3 extra contents videos in which I will introduce you to one of the most beautiful theories ever conceived by a human mind, the theory of relativity. In addition to learning the basic ideas behind this theory, we shall focus on some of its amazing consequences for space travel. At the beginning of the 20th century, Newtonian mechanics and gravitation was a very well-established theory that nobody dared to doubt. Nevertheless, there were two apparently unsolved problems with it. First, it seemed to be incompatible with Maxwell's equations of electromagnetism, and second, it predicted that two bodies separated in space could influence each other instantaneously through gravitation. A dilemma that had troubled Newton himself. Let us now focus on the first problem. Maxwell's equations predicted the existence of electromagnetic waves moving at a fixed velocity, the speed of light c, independently of the reference frame from which they were observed. This was clearly in contrast with Newtonian mechanics, for which the speed of any object must change with the inertial reference frame of the observer, according to the well-known Galilean transformations. In fact, according to these, if we change from a reference frame to another one, moving at speed v with respect to the first one, the observed velocity u prime in the new reference frame is given by the velocity in the old reference frame u minus v. At the beginning, scientists were more prone to believe that Maxwell's equations worked only in a privileged reference frame, the luminiferous ether, rather than to contradict Newtonian mechanics. This implied that light rays moved at the predicted c velocity only in one very special inertial reference frame, and would transform according to Galileo's transformations when changing reference frame. However, in 1887, Michelson-Morley experiment, also known as the most famous failed experiment in the history, could not prove the existence of this header. In this experiment, it was demonstrated that light moved at a constant speed with respect to the observer, regardless of its direction of motion and of the velocity of the observer. So, a question naturally arose. Did the luminiferous ether really exist? It was Albert Einstein who first made the big mental effort to think that the correct transformations between inertial reference frames were not Galileo's, but rather those which made Maxwell's equations invariant. This means that, under such transformations, Maxwell's equations retain their appearance in any inertial reference frame, and that therefore light moves at a constant speed c equals to 299,792 kilometers per second in any inertial reference frame. These transformations are known as Lorentz transformations after the name of the scientist Hendrik Antoon Lorentz, who discovered them in 1900s. The theory of special relativity, published by Einstein in 1905, is based on this awareness, and more precisely on two major postulates: the constancy of the speed of light and the fact that the laws of physics must be the same in every inertial reference frame. The consequences of such assumptions are amazing, as we shall see with a simple example. Imagine an observer on the Earth and an astronaut who is traveling very fast at a speed v close to the speed of light. The astronaut generates on board the spacecraft a flash of light perpendicular to the spacecraft's speed that reaches a mirror and is then reflected back towards the source. If the distance between the light source and the mirror is d, the astronaut will measure a time delta tau equals to 2d over c for the light to reach the mirror and be reflected back. However, for the observer on the Earth, the distance traveled by the light is not only 2d, but it's bigger and given by this expression over here, where delta t is the elapsed time for the Earth's observer and v is the velocity of the spacecraft. This is the distance traveled by the light, which moves at the constant speed c also for the Earth observer, so that we get the following equality. If we substitute the distance d into this equation, we obtain the relation between the elapsed times for the two observers, in which the factor gamma is known as Lorentz factor, as it appears also in Lorentz transformations. The astonishing conclusion of this analysis is that a phenomenon is always shorter in the reference frame where it begins and ends in the same location, which, in this case, is the astronaut's spaceship. Therefore, the time in a moving reference frame appears to be flowing more slowly simply because it is in motion, and this time dilation is higher the closer to c is its velocity. For consistency, it turns out that if time runs slower in a moving reference frame, the length of moving objects must contract as well along their direction of motion. This length contraction is again characterized by the same factor gamma. Now, let's apply what we have just learned to space travel. Imagine that an astronaut sets out to visit the closest star system to the Earth, Alpha Centauri, distant 4.3 light years, which means that it takes light 4.3 years to reach it. Imagine that it travels at a speed of light, at a speed equal to 90% of the speed of light. Then the factor gamma is equal to 2.29, and therefore, while for an Earth observer the travel would last 4.83 years, for the astronaut the travel would only last 2.11 years. How can this be explained from the astronaut's point of view? Well, in his reference frame it is Alpha Centauri that is approaching him at 0.9 c. So the imaginary line which connects the Earth and Alpha Centauri shrinks down to 1.9 light years. So from the astronaut's perspective, the travel is shorter because the distance is smaller. Let us now broaden our perspective and consider a travel to the Andromeda Galaxy, distant 2.5 million light years from the Earth. If the astronaut traveled at 99.9999999% of the speed of light, then the travel would only last 11 years, versus the 2.5 million years elapsed on Earth. So, if he ever returned to the Earth with the same velocity, it would have aged only 22 years, while for the Earth, 5 million years would have passed. Traveling at a speed sufficiently close to the speed of light thus enables traveling to any corner of the universe within a lifetime, no matter how distant. As we have seen, it also makes time travel into the future a reality. But is it possible to reach the speed of light? It turns out that, in special relativity, Newton's equation of motion has to be corrected. The linear momentum of an object now takes the form P equals gamma m0 v, where m0 is called proper mass or rest mass. Its rate of change is again proportional to the applied force F. Now, however, P depends explicitly on the body's velocity through the factor gamma. As the velocity approaches the speed of light, the gamma factor diverges to infinity, so that the only effect of a force parallel to the direction of motion is to increase its kinetic energy, but not its velocity. This video shows the evolution of the velocity of a rocket accelerated by a constant force F, for which the initial acceleration is the standard gravity acceleration g0. After an initial phase of constant acceleration, the rocket velocity only tends to the speed of light c, never reaching it. As a consequence, no object with a finite proper mass m0 greater than 0 can reach the speed of light, as this would require an infinite amount of work by an external force. The theory of relativity thus prohibits that any object with a non-zero mass travel at a speed equal or higher than the speed of light. When a body approaches the speed of light, its inertia to acceleration thus seems to diverge. So we can introduce a relativistic inertia to motion, also known as relativistic mass, as m equals gamma m0. If we multiply such a mass by c squared, we obtain Einstein's most famous equation, E equals mc squared, which formally states the equivalence between mass and energy. Such total energy can be divided into two contributions, the rest energy E0, independent of the body motion, and the kinetic energy Ek equals gamma minus 1 m0 c squared, which, for velocity much smaller than the speed of light, can be approximated with the well-known formula Ek equals 1/2 m0 v squared. As a matter of fact, it turns out that such an expression is only valid when studying non-relativistic motions.